Welcome back to Air Quality Matters. I'm Simon Jones, and coming up, a conversation with Ben Jones, Associate Professor at the University of Nottingham and one of the authors of AM10, a CIBSE guide to natural ventilation in non-domestic buildings. You might have noticed a couple of weeks hiatus there in the podcast. Sometimes, with the best will in the world and a one-man show, travel and guest diaries simply don't marry. So it was better, I thought, to take a break, get a few in the can, as they say, and come back strong. So we have some great guests lined up over the next few weeks, so welcome back to the show. I caught a presentation the other day organised by CIBSE to launch the release of AM10, some 10 years since the last revision. It was a fascinating presentation by Ben and Chris Idden, the two main authors. It really got me thinking about natural ventilation again, the benefits and challenges of an approach to ventilation as old as architecture itself, yet still leaned on today in some of the most advanced buildings in the world. And as these things go, I happened to be in Madrid last week, and who was there but Ben? So I grabbed him by his typically smart suit lapel and dragged him into a side room to get the 101 on this latest document. The philosophy behind it, his history with natural ventilation, and the whys and wherefores of natural ventilation in 2026. What place does this approach have today, and some of the fundamentals we should all think about? I think this was a really interesting episode on a very relevant document on a really fascinating part of ventilation. So don't forget to check out the sponsors in the show notes and at airqualitymatters.net. This is a conversation with Ben Jones. So who wrote AM10 then? Was it just yourself and Chris, or was there a team of people pulled a load of stuff together?
Initially, there was a team of people, but for various reasons, that was whittled down, and eventually somebody had to write it, and that was me. And evenings and weekends disappeared for a couple of years over a period of time. Chris did, he led chapter 3, which was on the systems thinking for AM10, particularly the control strategy and the various components you need in order to make a strategy work. But I worked with Patrick Sharp on sections 2 and 5 predominantly, and then section 4 I wrote and shared with the rest of the committee. So section 2 is like an introduction. It's almost like a bluffer's guide. Anyone who is vaguely interested in the subject could get as much or as little as they want from it. So if you're a salesperson, you've got to sell these things and you just want the basic knowledge. If you're an architect and you want to be able to make sure that the engineer you're dealing with is competent, there's questions in there you can ask them to make sure they know what they're talking about. If you're a student and you're coming to the subject for the first time, it's pretty intimidating, I think. I certainly felt that way when I read AM10 2005 when I was doing my PhD. I found it quite difficult to get to grips with. There was nothing in there that sort of said it in layman's terms, how the physics works.
So for people that don't know what we're talking about, AM10 is a guide to natural ventilation.
It's an applications manual, which is a way of showing you how you can do something, but it's not prescriptive. It's designed to help you make the thing, understand the thing, which in this case is a natural ventilation system, but it won't tell you exactly what you should do.
And why now? Why was it being written now? Because it was good 20 years ago, I think, AM10, the last one.
2005 was the last one.
Yeah.
First was 97, and that was a very different document to the one that was published in 2005. And I think the 97 document had a little more description and certainly had a lot of case studies. Case studies were taken out in 2005 because the feeling was that people were following them too rigidly when they were only meant to be examples of what you can do, but of also things that can go wrong, and that was conveniently ignored. And there is always a danger of putting case studies in, so we haven't put that many in. We haven't sort of addressed whole buildings and broken them down. We've just shown very small elements and how they might work together. So after 21 years, there's things that people don't understand. There are, of course, errors. Already found our first error in the 26 version. We'll be checking for more, I'm sure, over the years. And then there's advances in our understanding of the physics and the fact that we're doing things slightly differently, and the fact that buildings are evolving slightly differently. In 2005, we were just starting to think about sustainable development. Were we thinking about modeling for 2050 for climate change targets? Probably right at the beginning, but now that's something that's just done as standard, and that we need to make sure that we allow those reading and using the document to do that.
And for people that don't know you, you come from this, don't you? I mean, your first gig, I think, was in natural ventilation. So, like,
Huh.
this is something that's close to your heart in a
Yeah,
lot of ways.
right.
It's something I guess you would have referred to those original
Can
documents
I can
as
I
you were coming
name
up through.
can I
Yeah,
name
of
names?
course you can.
Yeah,
Yeah, yeah,
so I was sponsored by Monodraft to do my doctorate, and it was done in industry for industry. So rather than being stuck in a university, it was stuck. Being in a university with lots of other doctoral students, I was embedded in the company, helping them understand their products better so that they could make a better product, sell more of them. And they do, and they sell plenty, and they work. And we now, by the time I left, we had a whole bunch of tools that enabled them to work with their product
And
better.
what period was that then?
So
What
that
kind
was
of year?
2005 to 2009. And
So
then
you were doing that just as AM10,
the
the
first one,
second version came out.
that's
Yeah.
right. And then I did 2 more years with them in their research and development department. We were working out how to make their wing catcher product less aerodynamic, which may sound like a very weird thing to want to
Yeah.
do.
But it's got to catch, right? So we've got to catch
Right.
air. Yeah. You
Yeah.
don't want it missing air.
No,
Yeah.
no. Uh, they used to sell I'm sure they still do, a circular one which had spoilers on the outside. But the best shape, the most unaerodynamic shape, is a square. So we were putting fins on the edge. We were closing louvers to stop rain ingress, and making their louvers more watertight. Oh, watertight, totally watertight. So it was a much better product.
Yeah. So has it been interesting kind of looking back, going into this document now in 2025, I guess over the last couple of years as you've
Yeah.
been reviewing it, coming from where you've come from with the knowledge you've acquired over that time, going, right, okay, if I was right, I am writing this document now. What would I have wanted to see back in 2005? Looking at this, and scratching my head about this AM10, going, that doesn't make any sense, or that's wrong, or whatever it is.
Yeah. I think sometimes, some of the best textbooks I've ever come across are written by academics from, how do you say this, less elite universities. And maybe that's to do with something about the skill set the student they're having to educate. But I think I wanted to make AM10 a little more like some of those textbooks, where you just give endless examples, talk everybody through it, you use the same process in the same way every time, and hopefully eventually it just sort of sinks
Yeah.
in.
And you've spoken to me about the kind of philosophy behind the structure of this, that there was
Yeah.
layers. You were kind of intimating that chapter two was kind of the entry point into this. Explain again to me the kind of the layered approach here, where as someone like me that's just got a passing interest in this with some technical capability might want to read chapter two, but if you want to get into controls or into the math, like, it's all in there,
Mm.
isn't it?
Yeah, you can take as much or as little as you like. Yeah, there's
Yeah.
not a lot of maths in chapter two, very, very purposefully. I think people find maths quite intimidating. They shouldn't, but that is the case, and that's what we're dealing with. So we wanted to just be able to describe physics. You should. They always say, don't they, that if you really understand a problem, you should be able to communicate that to somebody else very clearly, very succinctly.
Yeah, to a 12-year-old, a Labrador, or me. Like,
Sorry.
if you want to test your knowledge of something, if between my dog, me, and a 10-year-old get it,
Right.
you've explained it well.
Yeah.
Yeah.
I think too, when we started it, I taught it for a couple of years, and the maths can be pretty terrifying. And I used to teach from notes, and 2 years ago was the first time I delivered the lecture with no notes. It's taken me 10 years to get there, to have the confidence just to be able to talk about it with a pen and with a whiteboard. And I think this document has very much helped me teach my students. But if you want to go back to the beginning, so section 2, right at the beginning, it talks about obviously why we need to ventilate spaces. And it's primarily to dissipate heat gains in the cooling season, to ensure we have acceptable air quality in the heating system. And although most standards and regulations, our approved documents, focus on indoor air quality, actually you're not sizing these things for that. You're sizing them to dissipate heat gains in the summer because they require the greater flow rates. And so if you size them for the summer, you're going to be able to meet the winter criteria anyway. But there's a certain amount of refinement, because then you're dealing with cold air.
I was about to say thermal comfort starts to rear its head, I guess.
It does, yeah. Right. And there'll be a whole bunch of tools that go with the AM10 and enable people to think about thermal comfort. So then it goes on to say, okay, so that's what we want to do. That's where we want to bring air into the space. How do we go about doing it? And at a very basic level, we're talking about temperature differences between the inside and the outside. If you were to write it down mathematically, it would come down to density differences, but it's temperature for the rest of us.
So you're talking about buoyancy and stack effects and things like that.
Right, it's the old adage, heat rises.
Yeah.
But if you've got a building, and you've got two openings on it, one at the top of a building, one at the bottom, that warm air will move up and out the top, and it will draw cooler air in from the outside at the bottom. And there are many other permutations in between. You could put other windows in the facade. It could just be one single tall opening, in which case you'll get the cool air coming at the bottom of the opening and the warm air coming out of the top, and then this sort of mixing area in the middle. And that's actually one of the new areas of physics that we've got in. It's not new physics, it's just not been in AM10 before. So that's the buoyancy element to it. And you can reverse it, of course. You know, if it's hotter outside and it's cooler inside, then the flow will come in from the top and out the bottom. That's fairly logical, I hope. And what's interesting then too is if you've got more heat gains in the bottom, which is increasing that temperature difference, you get more flow. It's a self-correcting system. So on a hot day, it will, and as it starts to get heat gains, or if you have a whole bunch of people in there who are heating the space up themselves, it will start to correct itself by allowing more airflow through. That's a very helpful thing to have on your side.
It sounds easy. Right, but and one of the things that struck me about the presentation you gave is that at one point an image came up of a modern building with an atrium or an outside space and a series of internal windows, and you were kind of looking and talking about it, and then just off the cuff you went, and that won't work on the top 2 floors there. They didn't think about that. So although like physics will out, you know, hot air will rise and pressure differences will drive air through a building and all that stuff that you can engineer for, we don't build simple spaces often, and we architects get involved and aesthetics get involved and layouts get involved, and spaces get complex right quick, don't they? And that's where we start to see mistakes being made. And you look at it with some experience, you look at a picture and go,
that won't work.
That won't work.
Yes.
You know, yeah. And yet somebody, you know, and I remember we were dealing with a naturally ventilated building in Dublin there, and somebody had rather helpfully built one of these glass atriums on the outside of the building post-construction. So it created a lovely courtyard, glassed-in courtyard. But of course, all of the buildings all of the floors on the top part of the building now weren't ventilating anymore, or ventilating in a way that wasn't helpful. So this stuff, we can get it wrong still as well, can't we? Particularly with what we want to, how we want to design a building. So I guess there has to be some real fundamentals taught in AM10 to say, these are the things you've got to think about if you want a space to function properly.
Right. And, you know, just because you draw arrows that say you want the air to come in here and you want it to go out there, doesn't mean it will.
Arrows of desire.
Delinquent arrows.
Delinquent arrows,
one of our old colleagues used to call them. But here's the interesting thing. So if air movement's caused by pressure difference, it'll always flow from an area of high pressure to an area of low pressure. It's trying to equalize energy. So the pressure difference across a facade or an opening when the temperature inside is greater than the temperature outside, the pressure difference on the lower opening is different in sign to that on the upper opening. Has to be, otherwise it won't come in at the bottom and out the top. So it may have the same magnitude of pressure, and it will if there are only two openings, possibly. But the sign has to be different, which means somewhere up that facade there's a pressure gradient. And we know there's a pressure gradient. You know, you go up in an aeroplane, your ears pop, or you go to the bottom of the swimming pool, your ears compress, and then you have to equalize them. Anyone who's ever dived will know about that. There's a pressure gradient, and somewhere on the facade, that sign is flipping. And what we're trying to do as engineers is control that. And so if you draw your arrows, this flipping point is called the neutral pressure level. So we're then trying to control where that is. And you can have multiple, you can have many of them, and you can have a different one on each facade.
And you've got the dynamic nature of weather and seasons and global warming and all of these different things going on as well. So you're not dealing with a stable source either.
Right.
You know, it's not just the building physics, it's the dynamic nature of air and the environment.
That's true. Yeah. We've talked about buoyancy. We haven't talked about wind yet.
Yeah.
Wind adds a whole bunch more complexity. So the wind doesn't necessarily always blow from the same direction. The building may not be symmetrical in its shape. And so the way that the wind causes pressure differences on the facade is non-uniform and can be extremely difficult. And it's one of the reasons why, of course, that some designers choose to design out the wind, get rid of it. And the reason for that can be sometimes if the wind is blowing in one direction, it can actually support the buoyancy flow, can increase it. But if it's blowing in the other direction, it can inhibit it such that the flow collapses. And that's a big problem.
So why, you know, this is from a risk perspective and trying to manage uncertainty, why the hell would you look at natural ventilation at all? Because it's unbelievably complex. I mean, the basic physics is simple, like you say, warm air rises and pressure difference and basic fluid dynamics, but the lack of control of the drivers, the principal drivers of this, and the complexity of buildings anyway and users, it seems to me often when you look at it simply from the outside that you're taking on risk with natural ventilation that you don't necessarily need if you're using mechanical systems where you determine how much is enough, and if it's not enough you can turn it up a bit, and if it's too much you can turn it down a bit. Much harder to do that with natural ventilation, isn't it? Like why the hell would anybody even consider natural ventilation in a big complex building?
Yeah, many of my colleagues in America would say just that. Just stick a fan on it and duct it. But of course, you've got to put a fan on it. You've got to locate that duct. You've got to run it, clean it, maintain it, buy it, and then there's the energy and carbon penalties that go with it.
Yeah, and so it should be said we still don't get that right either.
No.
And
then I think there's sort of the attraction of the adaptive model of thermal comfort, which basically says that we're comfort-seeking animals. If we're uncomfortable, we tend to do something that restores our comfort. Now, in a rigidly controlled air-conditioned space, that's very difficult to do, other than putting on more clothes or drinking hot drinks or changing your metabolic rate. It's a bit tricky. Whereas we, certainly in our own homes, have spaces that we can control the airflow through in order to improve our comfort. And I guess maybe that's one of the reasons we like it. It's a space that helps us relate to our outside, to our sense of place and where we are. That's not always preferable. It's not always good, but it can be.
Yeah, I really like that, and I had Chandra Sakar on the
Yeah.
podcast, and we talked at length about the work that he was doing in Singapore, where they found that actually rigidly controlled environments actually had less satisfaction overall than environments that delivered a little bit of uncomfortableness, but people felt that they had control of that space, some agency in that space. And that's hugely underrated, I think, that if you're forced to confront the environment that you inhabit, you're forced to have agency in it, and there's power that comes with that and satisfaction that comes with that, and that's really important. Whereas these micromanaged automated spaces where it's rigidly
Right.
21 degrees, people overwhelmingly, when you design for the average, you design for nobody, kind of thing. Whereas in a space that's dynamic and changing, if you don't quite like it, you open a window a bit, and try
Yeah.
and alter the environment.
Right. So the two competing models of thermal comfort. There are many others, but the reason why these two are so successful is they're quite straightforward. So the heat balance model, where you control everything within an inch of its life, considers metabolic rate, it considers our clothing values, and then it considers four other things. It's four environmental parameters. So mean radiant temperature, air velocity, and relative humidity. And then in the equation there, where you calculate the comfort temperature, you completely ignore relative humidity, because that's deemed to be relatively straightforward to control. But when we come to the adaptive model, we're thinking about things like demographics, environments, cognition, context, very sort of touchy-feely things, a little more human, if you like.
Yeah, I talk about it on this show, and I still need to find where that image comes from. But there's that classic image of a Parisian cafe where everybody in autumn is sat outside the cafe with coats on,
Oh,
because it's
blankets over their legs,
because it's
probably.
relatively
Yeah.
cold compared to the summer that they've come from. Yet at exactly the same temperature and conditions in the springtime,
Mm,
everybody's sat there without the same level of clothing on, because relatively it's warmer than the.
yeah.
So although the environment is identical, largely, the response to it isn't.
Yes.
And it just goes to show how ultimately useless those very precise models are, because you don't take into account the context of the individual that's coming from a particular season, going, this is relatively cold to me and uncomfortable. How do you account for that in a model?
Mm,
It's interesting. You've got to
yes.
provide people with agency of the space, I think, and get them to get used to a certain level of discomfort. So you build tolerance, and you get people engaged in the environment. I think we lose a lot of that sometimes in the discussion.
Mm, mm.
Yeah, it's interesting. The natural ventilation is there's one of the things I was writing down before we sat down and talked, that natural ventilation is as old as architecture. That this is
Yeah.
something we've been doing as long as we've understood the spaces we've been building. Originally for fire, we had to clear smoke out of spaces. If we didn't last very long. But over time, natural ventilation was an integral part of every space that we occupied. Um, what are we fundamentally getting right and wrong with natural ventilation now in 2025? If somebody was starting to look at this space from scratch, what are the kind of things they should be thinking about at a fundamental level to be coming out the other side of this with good outcomes?
So there are probably sort of about four things I need to think about straight away, because one of the reasons for section two is that keyword feasibility. Is natural ventilation right for my building right now? Because if it isn't, you're going to save you a lot of time, heartache, and money by switching to a different type of system. But it may be that natural ventilation on its own is not the right system. Maybe you need to link it with some other technology. Maybe there's some of the time where you have to add fans. Maybe there's some of the time where you actually have to seal the building up and cool.
Yeah, so there are some kind of fundamentals where you
Right.
just look at a space and go, this is just not the right picture to
Exactly
start
that.
with. Yeah.
So um, when you think of a building, when you think about the spaces inside, there are two ways we can categorize them. first is you can just think of a room on its own. So these are what are called isolated spaces. And those rooms on their own can be naturally ventilated, and each room will need its own design. And you're probably going to use a window, you might use a wind catcher, you might use a stack, you might use clerestory windows, but there are different ways of doing it. Sometimes there's only going to be an opening on one side. And the height to depth ratios have been in AM10 forever. I think, I'm not sure that they were in the 97 edition. They certainly were created by the 97 edition. But that basically says if you're using a single window for an isolated space, should only be twice its depth should only be twice the height. If you want to use two openings, a low and a high, then you can increase that to 2.5 times the depth. If you want to get a deeper plan space, to up to 5:1 height to depth ratio, you've got to have an opening on opposite facades. Now, you go much beyond that, the air will lose momentum through the space. You'll actually end up with two single-sided spaces, and then a bit in the middle where nothing happens.
Yeah, and these two reacting completely differently depending on wind direction. And
exactly that. And so just geometry. Now you can get around that. You can connect two 5:1 ratio spaces with an atrium in the middle and extract the air through the center. You can do that. So you can get a much deeper plan space, but you've then got to have a central area where the air can meet and exit from the building. So if you want a really deep plan space, it might not work for you. That's when you might start needing ducted air with fans. Then I suppose it follows that you've then got to have clear flow paths for that air to move. If you're just going to have a door, then that's a problem. Now we're in a space here the viewers and listeners can't see, but under these glass doors that I'm sort of pointing to here are open vents.
Yeah,
there's a way of allowing air to move from the office space into this sort of lounge space we're in, and I don't know whether they open up above us, but maybe they do.
There's an atrium of some description.
Yeah,
yeah.
But that's there to allow the air to move through. So somebody's thought about it. Someone's drawn an arrow and then said, "How can I get that arrow to be realised?"
And that's very difficult to do. Often with spaces that now have fire standards and regulations, where you have compartmentalization and this kind of stuff. There's levels of complexity here to the free flow of air through spaces that natural ventilation often comes unstuck with, isn't there?
I mean, that kind of ties into two things there. So there are constraints from you put an opening in, there's a noise issue, there's a security issue potentially, but there are now firms who'll sell you acoustically lined vents that go inside spaces. They may not be in the door, almost certainly won't be, but they're there and it can be done. But you need to know about it. You need to know to look for it. Otherwise, it's not going to work. And then I suppose there's another issue. What if the air quality outside is really bad and there's nothing you can do about it and it's not going to get better anytime soon? Then you probably need to seal the space up and filter what you're bringing in. That's why we call it outdoor air and not fresh air.
Yeah, and that's the other thing with natural ventilation is often we're not in complete control of the direction of flow of air in a space. So particularly with cross ventilation. So if you've got areas that are where the pollution is being generated, we've understood this, I think, better because of the pandemic. If we've got potentially infectious spaces, that air is then moving into other spaces.
Right.
There are challenges with that you have to start thinking about the movement of unwanted pollutants from one space to another.
Yes.
And we see this in homes all the time with damp and mold, moisture being generated in wet areas that are then being cross-ventilated and drifted out into other spaces of the building and condensing. Yeah, so it's not necessarily just like infectious aerosols. It can be moisture, it can be VOCs, it could be particulates from cooking, all sorts of things.
Yes, which is why managing your space is very important, and why some designers may choose to isolate spaces. And within a building, if you've got somewhere like a chemistry lab or some manufacturing where dangerous chemicals are being produced, you may want to mechanically ventilate that space and leave the rest to be naturally ventilated. It's perfectly possible to do both
I'll have you back to the podcast in just a minute. I just wanted to briefly tell you about Eurovent Certified Performance from Eurovent Certification, a partner of the podcast. We all know HVAC systems play a vital role in improving indoor air quality. However, there is a risk that some products may not live up to expectations. Even the best installed and maintained HVAC equipment can underperform if data used to specify products and design systems is incorrect. Consequences can include poor indoor air quality, increased energy consumption, increased maintenance, system failure, and non-compliance with regulations, and that's bad for everyone. However, there is a way to ensure products perform as advertised and deliver good, sustainable indoor environments. Selecting products holding Eurovent certified performance ensures that the manufacturer data has been independently and impartially verified. Eurovent certification's stringent certification process not only guarantees product performance, but energy efficiency too. I met some of the Eurovent certification team back in January at the Indoor Air Quality Matters conference and was seriously impressed with what they're trying to do. Their core aim is to create transparency in the industry by making certified data freely available. This means you can directly compare the performance of products to make informed decisions. Their certified product directory holds vital information on everything from air handling units to air filters. So don't take a chance on unverified products. Trust in proven performance. Details, as always, in the show notes at airqualitymatters.net and at Eurovent Certification. That's www.eurovent-certification.com. Now, back to the podcast.
Yeah, the thing about the outdoor air I think is interesting is because that's a dynamic I think we understand better now than we ever have done, that outdoor air isn't always necessarily fresh. And if we're trying to get good outcomes, particularly from particulate matter, which is, one of the, through your work, and harm intensities is one of our biggest concerns, especially with the oxidative potential of traffic related particulate matter. That's the kind of thing we really want to think about in spaces. So it isn't, natural ventilation presents some challenges with that, with filtration of outdoor air.
Yeah, so you're not going to be able to filter the air as it comes into the space as you would in a duct. Doesn't stop you having an air cleaner in the space though.
Yeah, very true.
And that would still, so yes, the contaminant is then mixed in the space before it's removed. It's not ideal, but it is a way of dealing with that contaminant.
Yeah, and is that something you deal with in AM10, is these kind of hybrid scenarios where you might have, a bit like 241, started to consider equivalent air change rates and filtration of spaces as an additive to outdoor air. You've got air cleaners. We're thinking about spaces in a much more grown-up way than we ever have done. Did AM10 start to think about the space in that way as well, this kind of dynamic model?
Actually, we when thinking about things like air quality and thermal comfort and so on, we stripped out material. One of the things we were very cognizant of is that there's so much repetition within some areas of the CIBSE literature. And the problem is, when one document is updated with new ideas and new thinking, you're then left with something that's hugely outdated everywhere else. So if you want to talk about air quality, you should have an air quality manual. If you want to talk about thermal comfort, you should have a thermal comfort manual. But there are things in AM10 that are very specific to AM10, to naturally ventilated spaces by definition, and therefore we do talk about those. But more and more, we're just trying to direct people to other places.
That's really interesting. Yeah, you're not trying to be a silver bullet document for all people. Like this specifically deals with natural ventilation. If you want to go and talk about air cleaners and filtration, that's another document.
Yes.
Yeah,
because that's evolving all the time, very rapidly.
Yeah.
Even the way. Anyway, that's a completely different conversation.
So what did has anything dramatically changed since 2005? So is there some stuff that you've gone back to and gone, well, that needs to be rewritten? We've learned something completely different in the 20-year period. Has there been some profound shifts within the document, or is this mostly being tidying and rewriting and trying to lay it out more logically, or has there been some fundamentals?
Yeah, some new stuff in. So section 5 is the calculation methods, a long description of the physics. It's kind of textbooky, actually.
Yeah.
You know, we start off by talking about, well, here's how you describe a pressure gradient in the space, inside, outside. Now, how do you subtract one from the other to get the pressure difference across a facade? What happens when the wind blows? Well, you can add this term in. Then you've got a pressure difference equation. Now, when you've got pressure difference across an opening, you need an equation to calculate the flow through that opening as a function of the pressure difference. And there's a slight change there. One of the key areas is the way we treat areas. So if we just had a round hole in a space, you and I could take a set of calipers independently and come up with pretty much the same area. But as soon as you get to something that's a little more complicated, maybe there's louvers. Even more worse, perhaps, would be storm louvers, which have really complicated geometry. And your way of estimating the area of those things and my way, neither of them would be wrong, because there is no official way of doing it. But that's the problem. How can we take that problem away? Well, one of the ways we do that is to combine a very simple free area. What if you've got a window? What's its width? What's its height? That's its area. But we can combine that with what we used to use, which is the discharge coefficient, which is the resistance to airflow bound up in a single non-dimensional number, and multiply it by that free area. And so we just call that an effective area. So we use one term rather than two terms. And it stops people fiddling around with it. It stops people making mistakes. It pushes window companies and opening companies to actually measure the effective area of their products so they know how it performs aerodynamically. And many of the good companies are doing that already. All of the good companies are doing that already. So they would know that. But it also then enables engineers to be able to differentiate between companies who do and don't know what they're doing. So that's one. Then there are the equations that were in the last version used to size single-sided openings were pretty basic. As it turned out, it did work in some conditions, but there were quite limited conditions. So I talked about that area of recirculation. If you've got a large opening, when there's buoyancy-driven flow, your air coming at the bottom, some at the top, and where it flips sign, the pressure flips sign halfway up, there's this area of recirculation. So as some air wants to leave, it's actually brought back in. So you actually end up with two parts of the pane or the window that are allowing air in and out that are less than the height, because you've got this area mixing in the middle. So we account for that. And we do that not just for buoyancy, but for wind. So when the wind hits the surface of a building, it turns sideways. So you've got this parallel flow. So now we deal with this turbulent mixing flow with this parallel flow. And it just means we should be getting openings on buildings that are better sized, that they're not going to be undersized. And that's always been a problem. Buildings that overheat because the openings have been undersized before.
So some of this work that you're doing, where you're getting into the real core math of natural ventilation, is this the kind of stuff that anybody is actually working with, or is this now material that's going into models? So is some of the work that you're doing in AM10 actually feeding into the software that designers and engineers would be using, and so you're fundamentally changing some of the actual math that's going in to some of this stuff? Or is the stuff you're kind of talking, you expecting somebody to be getting a calculator out and making decisions about a window or about a stack or an atrium? Or is this really the kind of stuff that's being fed into some program or another?
Well, it might be. And I would have thought that some of the software companies might be interested in it if they haven't got it already. But this kind of thing's already in very academic-y kind of tools like Contam, probably in Energy Plus too. So it's already there.
Yeah.
And there are ways of dealing with that. But I think For somebody who's doing this regularly, they only have to build their spreadsheet once. And they need a spreadsheet for sort of first pass estimate of opening areas. Then they'll take those out opening areas, and then they'll do some more detailed estimates with them. So they might go into their dynamic thermal model then to look at whether you're going to get overheating in the summer. Are you meeting your air quality regulations in the winter?
Yeah,
And if not, you go back and you tweak and you try to find out why not. It's very important that this is done in software at the beginning, or just with mathematical models in a spreadsheet before you start building anything, because it's very, very difficult and expensive to correct later on.
It sounds like this is a document that really is designed for the entire design team. That this isn't a document you've created that's purely for engineers or purely for architects. This is something that you expect to be on a shelf as a reference document in all sorts of environments.
I hope
Is that
so.
fair to say?
Yeah, I hope so.
Yeah.
I did mention at the beginning, you don't have to be technical at all. You could be in sales. You've got to know what you're selling.
Yeah, I mean, I always worry about the Dunning-Kruger effect with information, and people thinking they know more than they do.
Right.
So I think the particularly salespeople, they've got a job to do.
Yeah.
Shift gear, know, and we'll throw a few documents and terms around and standards and think that people know what they're talking about. But I get what you mean. Like it's interesting when you're creating a document like this, you always have to think about who your audience is. And so when you're creating a quite a general purpose guide like this, you've got to write it for every man, haven't you, really, to use that term?
Yes.
Every person.
So it is a CIBSE document.
Yeah.
So largely it's for engineers, but I think we know pretty well, given where it's contained and referenced in other documents, that it's not just engineers reading this. It's mentioned in approved documents, it's mentioned in LEED, it's mentioned in ASHRAE standards, and of course many architects use it because they like to use natural ventilation, so they need to know how to do it.
One of the interesting things I was thinking about as well is that this document lives in a very different world than it did 20 years ago. Environmental sensors are ubiquitous. Our ability to see the performance of the spaces that we're in is fundamentally shifted, hasn't it? So the evidencing the efficacy of some of these design principles is easier than it's ever been. So this world of natural ventilation and whether it's working or not is more transparent than we were back in 2005. That's for sure.
Yeah, the age of the Internet of Things, and there's no excuses there really. If you're measuring everything, then you should know whether it's working.
Yeah.
So long as you act on it.
Yeah, and that's the other thing. I mean, back 20 years ago, the driver for a lot of inputs into the system from a human perspective would have been driven by thermal comfort. But now we're able to drive inputs into that system because people may be able to visualize the air quality in the space. That it might feel comfortable, but you can see the CO2 deteriorating in the space and go, actually, I think this space could do with it more air. And then you can start to make those personal judgments as to whether you're sacrificing comfort for air quality. But at least you can make those choices with the visibility, whereas that wasn't the case back in 2000, or much harder to do back in 2005.
That most of the companies now have an override switch.
Yeah.
So you can just open everything. And that gives people agency, which is part of the adaptive model. Circle completed.
Yeah. Do you have a clear picture in your head what good looks like from a natural ventilation perspective? Do you come from this from a place where you have a clear vision of what good looks like? Because some of these conversations, the reason I say that is sometimes these conversations can be very theoretical, or you're talking about documents and standards or guides. But I think particularly like someone like yourself who'd come from this sector when you were in your formative years, shall we say, you have a picture. I think you have a mental clarity of what a good naturally ventilated space looks like. So we'd hope that this document is grounded in that reality, that out the other side of this, there are genuinely spaces that can perform and be comfortable and healthy and the things that we want those spaces to be.
Right. So it broadly is that it doesn't overheat in summer, and that in the winter the air quality is acceptable, but without freezing everybody, so that thermal comfort is preserved. And then it comes down to architecture and fitting it in with other things.
Yeah.
So because if the space is rotten, then people aren't going to like it. But generally, there's plenty of evidence to say that people like being in spaces that they control, and the only way to do that really largely is with a naturally ventilated space.
Yeah, it's funny you should say that. I was only talking to somebody this morning about my experience recently at the other end of the spectrum in these highly curated spaces. I was in a building in central London for a healthy buildings conference, and this was a building that's touted as being one of the most technologically advanced buildings in London. I mean, it's got an entire floor dedicated to how amazing it is.
All right.
You know, one of those spaces that's got screens and demonstrations of the engineering
It's
and
very
stuff.
happy with itself.
Very happy with itself. Yeah, really, really. And it's got screens on the entrance into every meeting room, and it's fabulous. From a technology perspective. But I was there to do a panel discussion, a bit like we've been doing today, and I came in at the end of the day, and as I walked into the main auditorium, a space that was clearly designed to hold 150, 200 people, and it was probably about 100 people in there. As I walked in, the screen said 3,200 parts per million CO2 as I walked into this space.
Oof.
So I went to the desk and I said, there's something wrong with our room. I'm surprised that there isn't stuff happening. And so I went into the space, and that people had fire doors jammed open to try and get air moving because it felt stuffy, obviously. And somebody made the mistake of asking the question, what do you think of these kind of green labels and technology labels for air quality? And I said, they're great, but we've found ourselves in a position where you've got 100 or so of the leading health experts on air quality in a room at over 3,000 parts per million, jamming fire doors open in one of the most technologically advanced building in London. Something's fundamentally broken here that nobody's put their hand up and gone, this is unacceptable. Like, how have we ended up with, you can have 100 experts in a space and nobody's gone, hang on a minute, so it's someone like me has to call it out.
Yes.
And everybody's kind of nodding furiously, and you're going, that's the risk of automation, because nobody feels they have agency in this space. What are you going to do? You've got to get into the algorithm and the system to try and fit. You don't have control over this space. The only control you had was wedging a fire door open. And that's the risk of automation, I think, is that if you lose that agency, people are sitting in a space where there isn't an openable window.
Right. No one's checked it, clearly.
And nobody's checked it.
Nobody's thought to say, is this space running correctly?
We've assumed because it's got a badge.
And there's no feedback either, I guess, saying, hold on a minute, this is a bit high.
Yeah.
Very high, actually, at 3,000 parts per million. Must have stunk.
It did. I mean, I came in because I was doing a bit like today, I was doing interviews around it. So I came into that space at the end of the day and went, this is rotten, and this stuff really matters. And I made the point at the time that, at best, a dozen people are going to go home with a tickly cough they didn't deserve. But at worst, 3 of those people are taking that home to a vulnerable person that can't afford that.
Yeah.
So this stuff matters. Like, this is chipping away at your future health and well-being. But at worst case scenario, that this could be somebody that can ill afford to be picking up a virus or a bug because this space isn't performing. So we've got to get better at calling that out, I think.
We take a cost from MOT every year. Why don't we do that with buildings?
Yeah.
Well, the building regulations are there, but they're not enforced after the building's been handed over, are they?
Yeah, that's true. Yeah.
Chris, my co-writer, highlights there's some countries who do it. Sweden does it with some of its mechanical systems in homes. They're checked frequently. Why are we not doing it? What's the point in measuring all this stuff if we're not going to actually use it to check whether it's fit for purpose? That goes on to perhaps post-occupancy evaluations. You give your building a good 6 months and then check that it works. There are a number of ways you can do that, but it seems that nobody wants to pay for it. That's the big thing.
I think that's an issue with the construction industry in general. I've had several podcasts recently where the general consensus is it's one of the few manufacturing processes in the world where there's almost zero feedback loops in performance.
It's linear, isn't it?
Yeah, you build it and you run as fast away as possible from that product and put as much distance as you say. You know, all the developers, the architects, the engineers, they're all indemnified up to the hilt just to get as far away from that product, and they don't learn anything from it, and then they repeat the mistakes again and again. You know, that and that's the challenge with, you know, things like these documents, isn't it? You have to write them in a way that makes them accessible, where people can learn and take on new knowledge, but also realize that this stuff matters and is important. I guess post-occupancy analysis, was that part of this as well? Or was that another document as well?
No, I don't think there is another document that talks about post-occupancy analysis. When I teach it, there's a chapter that Momovic wrote about, I don't know, 10 years ago, with some of the co-authors from the original BB 101. And that's pretty much one of the few references I have on it and how you should go about doing a decent POE.
Yeah. BB 101 was again had quite a big natural ventilation component. For people, for listeners, that's a document that was around education for schools. So if you're from the UK and you're involved in anything to do with education, you'll know BB 101. But that had a big natural ventilation component as well, didn't it?
Yeah, that's the statutory document by proxy, because it's mentioned. It's DFE's, Department for Education's own document. It promotes natural ventilation as a solution. And as such, it actually gives natural ventilation a bit of leeway over mechanical ventilation.
Yeah, I saw that. And so for reference, things like parts per million thresholds are slightly different for natural ventilation than they would be mechanical ventilation. As one example.
Interestingly, that's a document that doesn't prescribe flow rates. It prescribes carbon dioxide concentrations. Because, if I remember rightly, it's easier to measure a CO2 concentration than it is to measure a ventilation rate. And because there's correlation between the two, you can infer one from the other. And they were happy with all the uncertainties of
Is there any of that in AM10 that you really are doing this based on outcomes, that there's a performance side to AM10 that you can start to give some guidance on what expected outcomes should be? Or is this more fundamentals and prescriptive is the wrong word, but you know, the math behind the flow rates and the designs and so on? Do you talk or get into the weeds of this is what you should expect a space to do if you do this right?
We size our openings. So the way I'll answer is by saying yes, how we size our openings using a delta T, a temperature difference of 3 Kelvin. And that's there to dissipate our heat gains. And the reason we do that is because in the middle of summer, you've got the smallest temperature differences between the inside and the outside, and the wind doesn't blow a whole lot. So we tend to just size our openings purely on buoyancy and for a delta T of 3. That works up to a point. And when you get too high, then you can get quite hot inside, and it may even be hotter outside than it is inside, and then you get problems there. But that may be a point then where you need an additional ventilation system. That's how we're telling people that how you know these openings are big enough. They are big enough when you can dissipate all your heat gains in the summertime with a delta T of 3, and you can calculate the flow to dissipate your heat gains, required to dissipate your heat gains when you know what your heat gains are.
I'm assuming then this is a document very much for its region. That the stuff that you're applying here isn't going to work in Madrid, for example, where you're not going to dissipate heat gains when you've got very high temperatures outside.
Well, you might. You know, if you travel further south towards Malaga, you've got Alhambra at Granada, which is a beautifully naturally ventilated space building, which has been. You have to remember this technology didn't. Some of these technologies didn't originate in Europe. The first builders of stacks were termites, who manipulate openings on their mounds to allow air in at the bottom and out the top in order to manage moisture content where they are farming fungus, which they then eat. And not many termites in Madrid or in Nottingham for that matter.
Yeah, I mean, when you think that through, it's a silly statement, really, because we've been building buildings that are performed in hot climates for
plenty of thermal mass. That's why they work. Yeah. So when the sun's very, very strong, it takes a long time for that energy to get into the building. By the time it gets into the building, the temperature has dropped a lot, and then you can start to dissipate those heat gains from your structure at night.
Yeah.
And that's done with the wind catchers of Yazd in Iran, and many other spaces in that region, Pakistan, India, and so on.
But I think this all comes back to, you've got to think of this at a fundamental level from the ground up with buildings. This isn't just something you come in and cherry pick. And I've always heard people that talk about, the successfully naturally ventilated schools and things that, this is a fundamental design principle from day one, that people that know what they're talking about are, deeply ingrained with the design of this from the very beginning. Then those spaces perform. Yeah,
it's not nice to have.
Yeah, but if you think you can chuck a passive vent on a normal classroom and you haven't thought about natural ventilation, good luck.
Yes.
Right, yeah, sticking in a few skylights and a couple of high and low windows, it ain't going to cut it. You might get lucky, but...
Yes, I would agree with that. It needs to be thought about as part of from the design team, on a round table, between all those involved in building that building and coming up with the design and critiquing that design very, very early on in the design stage.
Yeah. Where can people get this document? On the CIBSE website, I take it?
That's it. It's part of the CIBSE Knowledge Series. All their documents, it goes alongside their guides A to C, there are more guides than that, but that's where the application manual sits alongside, and if you just type in AM10, it'll come up.
You will pay for this document, I think, but that encourages you to join CIBSE.
Well, if you've joined CIBSE, it's free.
Yes, exactly, yeah.
And everyone should join CIBSE, of course.
Yeah.
Chris and I are going to be touring around, maybe go and see a few CIBSE regional chapters, and for anybody else who wants us to go talk about it, we'll go promote. It can be done online, can be done in person.
Yeah, and we saw the webinar online, and that was a real treat to kind of get behind the scenes how this came about, how this document came about. And
there will be a training course as well.
Really? Okay.
Yeah, that's in the pipeline at the moment. We're talking about how that might work, how we might do that, how can we get people designing naturally ventilated buildings in a day.
Very interesting. Yeah. Well, how far
can we go
down the rabbit hole can you go in a day?
Yeah.
Well, I suppose it depends on people's capability. Like you could go gangbusters for 8 hours solid, but you might lose 40% of the room by about lunchtime.
Right.
Depending on how hard you go at it.
It wouldn't be the first time I've lost a room.
No, I think between you and Chris, there's a risk there. It gets pretty numbery pretty quickly. Yeah.
Well, the students sometimes you put an equation on the board and their eyes just cross.
Yeah. Well, these days, of course, now you just take a picture of it and you go, explain this equation to me, please. And it goes this, and this.
Right.
Know? Yeah.
I think that's extremely helpful, and everyone should be doing that. Use your generative AI to tell me what the terms are. Tell me why they're formed like this. If there's a step you don't understand, it's just brilliant.
It's so easy now to learn little bits. If there's something if you can't quite put the jigsaw pieces together, that generative AI is brilliant for that. I mean, only this morning there was an equation put up on the board, and there was a bit of it that I couldn't understand why it was there. Took a picture, stuck it in, and go, explain that last bit to me. What are they trying to do with that? And he goes, well, it seems that they're trying to do this, this, and this. I go, okay, you sure, but what about this? And he goes, well, yeah, you could do this. And so, it's very good at understanding a formula.
Was that Valter's equation, mass balance equation, perhaps?
Might have been one of them, yeah. It was something like that. Whereas in the old days, I was only saying this to somebody, the old days of these conferences, I'd have to take a photo, I'd get back home, I'd send it to my engineer friend and go, could you explain this for me? Then have to wait for him to have the time to look at it and explain it to an idiot like me.
So I bet he'd have to look up a few things.
He'd look up, he'd email and explain it. Whereas these days, you take a picture and within 15 seconds, it's telling you exactly what you're looking at.
Yeah.
You know, you don't even need to give it any context. It will see it, and it's superb. Really good. Ben, look, thanks a million for coming out of the conference and chatting to me.
Pleasure.
I think really recommend people check out CIBSE website. AM10's the one to look for natural ventilation, and keep an eye out for the events that you're doing on it.
And can I just say, we're open to comments. What do we do well? What don't we do so well? What works? What doesn't? There'll be another version eventually. It may go on to a wiki eventually, but there's always ways we can improve this, and be helpful if we know, if we have some constructive criticism. So thanks for the opportunity to be able to tell people about it.
No, I was really excited to have this chat when I saw you had another go at AM10, because natural ventilation is something that I'm hearing spoken about increasingly more, actually, funnily enough. It seems to, I wouldn't say it's back in fashion, but it's definitely, I think there's, particularly as I have a more of a global view these days, there are parts of the world where natural ventilation has a really big part to play in better ventilation of spaces. So it's really interesting to see this conversation appearing. So guides that help people with the fundamentals that actually have to sit down and design buildings and get this stuff right is enormously helpful, I think. Ben, thanks a million. Really appreciate your time, mate.
Thanks for having me.
Thanks for listening. Before you go, can I ask a favour? If you like this show and can think of other people that might like it too, please do spread the word and let's keep building this community. If you can check 5 stars, I'd really appreciate that. Apparently, it really helps with the reach on some of these platforms that you're listening to it on. And of course, like and subscribe if that's possible too. Do check out our YouTube channel. There's plenty going on over there as well. These episodes are not possible without our sponsors, so thanks a million to Particles Plus, Eurovent, ACO and Farmwood. Without them, this just simply is not possible.